First reaction type that we're going to discuss is combustion reactions, which is technically or are technically defined as anything that's reacting with oxygen. And that really could be anything if the second product is O2. However, more typically, we're going to define it as a reaction between oxygen and a hydrocarbon. And the word hydrocarbon is just a fancy way of saying a compound, a molecular compound that's going to contain carbon and hydrogen, maybe some other stuff. If anything else, it might also contain some oxygen in this compound, and then also sometimes nitrogen. We're starting with combustion reactions because the products are always the same. There's only one question that you have to answer, and that is it a form of complete combustion or incomplete combustion? If the combustion is complete, and typically we are going to assume that it is, that means that it's the most efficient version. Okay, the products are always, and this is what makes it so easy, carbon dioxide and water. Okay, done. That's it. If you recognize it as a combustion reaction, you put carbon dioxide and water as the products, you balance it, you're done. If it's incomplete, however, the products are going to be carbon monoxide and water. Now, in reality, it's a little bit more complex than that. You would have more products than just carbon monoxide and water. You would have pieces of the fuel that were not completely combusted. You would have just spent carbon, lots of other things. But for simplicity's sake, we're just going to say carbon monoxide and water. And really, for our purposes, we're just going to assume that we're going to have complete combustion. What determines whether or not a combustion reaction experiences complete or incomplete combustion is the ratio of oxygen to the fuel. If you are lacking for oxygen, if your ratio is insufficient, that's when you end up going through incomplete combustion. That's what our cars do, by the way. Our cars are not our combustion engines, but they are not super efficient. And because they are unable to nail down that ratio of oxygen to fuel along with other things, that's why they end up producing a lot of byproducts that are undesirable. If our cars were perfect, they would go through complete combustion. They'd just make carbon dioxide and water. Carbon dioxide, yes, does pose its own problems, but we wouldn't have to deal with the other pollutants that the fuel produces. As far as examples go, it can be as easy as this one here where we have butane being burned. So butane, by the way, is C4H10. You know it as, or should know it as, tetracarbon decahydride. Okay, this is the organic name, butane. So if we have C4H10, notice it doesn't even say it reacts with oxygen, but if something is burning, right, I know that it has to be reacting with oxygen. That's a requisite for something to burn. Okay, so even if it's just as simple as this, you need to assume, oh yeah, I know that oxygen has to be part of that reaction. Okay, and I'm going to assume that it's complete combustion unless I'm told otherwise. So that just means I make carbon dioxide and water. As far as the phases go, this is a very exothermic reaction, which means it produces a lot of energy. So obviously our products are going to be in their gaseous phase. Okay, carbon dioxide is a given. There's going to be enough energy to make that water gaseous. Oxygen, you got to work pretty hard to not make it gaseous. And usually hydrocarbons are going to be in the gaseous phase as well. Just assume that it's a gas unless something tells you different. The most difficult part about combustion reactions is balancing them. And so really you just got to pay attention to the numbers. And it's really not that bad. So here I see that I've got 4 carbons on the left, so I'm going to put a 4 here on the right. And then I've got 10 hydrogens on the left and only 2 on the right, so I'm going to put 5. And then this is where I run into trouble. On the left I have 2 oxygens, on the right I have 4 plus another 5 is unless my math is terrible. There is no number I can put here in front of the oxygen to make that work. When this happens, and we talked about this in that first video, this is one of those instances where we have to go back and double the fuel. So I'm just going to put a 2 here. That's going to scale up the reaction. So now I've got 8 carbons. I was trying to be sneaky and write that light. It didn't really work. And now I have 20 hydrogens. So I need 10 water molecules to compensate for that. Now I have 8 times 2 is 16, plus another 2 is 26 oxygens. There is a number I can put here to make that work, and that is 13. Okay, so that's an easy example. Yeah, we had to double our fuel, but that's just counting. Remember, balancing is a guess and check process, so don't worry about that. In this next example, we've got something that should take you back to those glorious days of biology class. Good old glucose, C6H12O6. Explicitly it's going to react with oxygen. I didn't need to know. They could have just told me it was burned and I would have figured it out too. And again, we're going to assume complete combustion, and the process are the same. This is pretty simple. Okay, so carbon dioxide and water. Now, just because I know different, I'm just going to say that the sugar is a solid. But everything else is going to be a guess. Again, you can assume gaseous unless something tells you otherwise. And then again, all we need to do is balance. This one's a little bit trickier because the oxygen on the reactant side is also contained in the fuel. So you got to take that into account. So for instance, I've got 6 carbons. Okay, so I need to produce 6 carbon dioxides to make that work. I have 12 hydrogens, which means when this breaks apart, I'll have to make 6 water molecules. Okay, now I've got 6 times 2 is 12, plus another 6 is 18 oxygens. Now don't be hasty and just put a 9 here, because that would actually give you 6 oxygens too many. So I said I had 18 total on the right. Well, 18 minus 6 brings me back to 12. This is going to be a 6 as well. Okay, so again, most difficult part about combustion reactions, just balancing. That's it.